Hi, everyone. I am here to answer your questions on your reflections. And what I thought I would do, at least for the first couple of weeks, is just kind of read through and see where there's some confusion, where I can help. So I'm just going to go through, and if we repeat some, that's good. We'll figure out that, probably most of the class has the same kinds of questions. So the first question is confused about the specifics of the IDEA method. This is a great question. So as you know, we solve problems in this class, in this physics class, using IDEA: interpret, develop, evaluate, and assess. So the I part is the interpret part. Some of that is hard. All we want you to do is recognize what part of physics the question's asking you. In most of the cases, in the first problem sets, it's going to be things like one-dimensional kinematics, for example. Or it might be this is a free fall problem. We're just looking for one sentence that identifies what part of the textbook this problem's from. It helps you identify out of all of the different things that um, we could have asked you, what part of the book, what part of the class we're asking. Then D, develop. That's where we want you to write down what are the given uh, values of things in a problem. What's the appropriate equation? This can be tricky, but if you keep those 3x5 cards for all of those lectures, you'll be able to kind of narrow down what's the right equation. So for a free fall problem, that might be the free fall time, like the problem in which we asked, how long did it take Tom Petty to free fall from the top of the Sears Tower, right? That's something that you can figure out using the kinematic equations of motion, and you can look up the free fall time. Then evaluate. Evaluate is just putting in the numbers and then following the units so you get an answer that has the appropriate units. And then the last part of this, probably the most important and also the hardest to master, certainly was for me, uh, was assess. Is the answer right? Are you in the ballpark? Are you in the parking lot of the ballpark? Are you even in the right state for the game that you're watching? Some examples from the first group problem solving that we did on Thursday would be the correct answer is that you came to a stop. You needed to start braking at 102 meters away from the moose, given that you're traveling 45 kilometers per hour. That's a reasonable amount of distance. So a correct assess to that is, well, given what I know about stopping cars while you're driving at speed is, yeah, you need about 100 yards. A meter is about a yard to come to a complete stop, at least. Um, we are looking for things about like, are things that you expect to be positive positive? Are things that you expect to be negative negative? Are things really big or really small? If we ask you for a speed, is it greater than the speed of light? If we have a problem about someone walking and you're trying to find a walking speed, are they walking faster than any human being could ever walk? When we ask about time, does it take billions of years or a billionth of a second? Those kinds of things. We're looking for the correct use of units and rec your recognition that the answer is of the right magnitude for the kind of phenomena that you're studying. And that'll take some time getting used to. Some of it you'll know from personal experience, and some of it you'll get honestly from just taking this class. Okay. Let's see. Nothing here. How do you decide what is X naught and what is X in acceleration problems? Fantastic question. So in some of the problems that we did, we need to identify what's our initial position, X naught, and what's our final position, X. And so it all depends on the problem. And the same with V and V naught. So for example, in the second group problem that we did on Thursday, question was what was the acceleration required to stop a plane that was given you're given a certain speed, landing speed of like 200 kilometers per hour or something like that. So that's the initial speed because what the question is asking is how much braking power do you need to bring it to a stop? So if the question, for example, is asking you, um, how do you brake, right? You have initial speed, v naught in that case would be the speed given, and then the final speed would be zero. Okay, so it's all very context dependent, and again, that takes a lot of time. We ignore vectors in the notation for 1D problems. I don't understand why there's still directions. This can possibly due to being get the info about directionality from the sign and the number. That is exactly correct. So you will notice in class that I have suppressed vectors when I do 1D problems. And that's because in a 1D problem, all you're really talking about is going forward or going to the right or going to the left or going forward or going back or going up or going down. Putting vectors in there can just make things a little more complicated. It's not wrong. It's just that it's a little easier to have to understand that plus means, say, to the right, and minus means, say, to the left, or plus means up and minus means down. We'll see on Tuesday when we talk about projectile motion that we really have to be careful about using vector notation because there now we really care about going over and up, right? So when we have more than one dimension, we'll be a lot more careful about vectors. But remember that a vector is something that has size as well as direction. And that's what we're really trying to get at here. I get confused. Thank you, by the way, for that question. I get confused on drawing of the graphs from X to V to A. If we could just have one or two basic examples, I think that would help. That's a fantastic question. I happen to have a board to help amongst all of the toys. So here's my whiteboard. And the thing to remember is when we're going from X, that is position, to velocity to acceleration, right? We are looking at the change, the change in X, the change in V. Yeah. So as we move through here, we're looking at how they change with time. And when we're talking about how things change with time in calculus, that means we're looking at derivatives. And when we look at derivatives in graphs, that means we're looking at the slope of things. So for example, if we have a kinematic graph that looks like this. So here's X as a function of time, right? And we'll get it over here. Right. What this tells us, and this is similar to the first or the second question, I think, on the quiz this week, is how is X changing with time? Right. So this is telling us that we're starting at some position X equals 0, say, and we're going out a certain distance, say the maximum distance at the top of that. So call that X1, if we like, we'll call that X1. We'll call that 0. And then we come back. So this is an out and back, but we're not going out and back at constant speed. We're constantly changing our speed. And the way we know that is that at every point along here, we can take the slope. At every point, the value of that slope is the velocity. So when you have a steep slope, you could draw right underneath it a graph of the velocity versus time. And here, this would be a very large value, positive. So we could put a point right there. At this point over here, it's still positive, but it's a little bit lower, right? It's not as steep. So its slope is a little bit lower. So we might put a point here. And if we go over here, the slope is even flatter. That means it's even smaller. That means right over here. By the time we get to the top of this curve, the slope is 0 straight across, which means that the slope would be down here. And then on the other side of this curve, the slope is now negative and gets increasingly negative. So we would continue this line until we would have this straight line that goes from positive velocity to negative velocity. Okay, so all of this is saying is that at a given time, you're going to start with a very high speed, then you're going to go a little bit lower in the positive direction, a little bit lower, then you're going to stop, then you're going to have a small speed in the negative direction, and you're going to keep increasing speed. That's exactly what we just drew here with the X. If we wanted to tag on to this the acceleration, then we would want to take the slope of this line everywhere. But notice this is a straight line. So everywhere that we have, oh, my blues run out. Everywhere we have a point here, we'd get the same slope, and it's negative. So we would draw a straight line with a negative value. Okay, so that's connecting the motion that we see with these graphs. And as I said in class, there are two ways that you can interpret kinematics. You can use the algebra or the calculus, really, right? If you know what x of t is, right? If you're fortunate enough, and we love it, we love doing math. If you have x of t is some kind of function, then v is equal to dx dt, whatever that derivative is. That's awesome. But if you have the graph, that's the same thing as saying, well, what is the slope of that position curve anywhere? So if you can draw the curve, then figure out the slope. And you have a problem in the homework where you have a curve, of kind of complicated curve, and it asks you, how is position changing with time? Where is it speeding up? Where is it slowing down? Think of it this way. Remember that the slope is the rise over the run. So if you are increasing your distance by a large amount in a short amount of time, that means that you've gone really, really fast. And if you've gone far away, say, in a short amount of time, you've gone at a very high positive speed. If you've come back toward me in a very short amount of time, then you're coming back at a very high negative speed. If you only go an inch in an hour, you still have a positive velocity, but it's a very slow velocity. That rise is very low, so that slope is very low. So anyway, I hope that helps. If it doesn't, keep asking questions. All right, what else we got here? Bit confused on V average is equal to V instantaneous when A is a constant. It's not quite okay. So I understand the confusion. The thing that is equal when we have constant acceleration is that the instantaneous acceleration is equal to the average acceleration. Okay. And that's because remember that the average, when we talk about average quantities in kinematics, we are talking about final, right? So if we were to take a look at, say, x versus t, right? And we want to know what is the average velocity of this. All we care about is our final x, our initial t, and our initial or our final t. And in the book, we've been calling this t1 or x1, x2, t2, t1, right? Now, that's the average, right? All we are asking when we find out the average of something like this is what's the delta x, right? Delta x over delta t. How far total did you go over how much time? But there are a lot of different ways that you could go to get from that initial place to that final place. You could take a trip that looks like that, right? What that tells you is that you're speeding up, slowing down, stopping, turning around, right? All these kind of complicated paths that you could potentially take. And so if you go back to how we originally talked about this, and this is where the slope comes in. Again, let's consider a graph that looks like that, right? So we could find the average velocity by looking at that x2 and x1 and t1 and let's call t2 over here. And it'd be a very gross estimate, rough estimate. But if we broke this down into seconds, right, we could see that the speed is changing every second. This is kind of similar to the quiz question about my recent marathon experience. I didn't run at the same rate, but if you ask what was my average skating pace, it was 12 and a half miles an hour. My slowest speed was something like 5 miles an hour. My highest speed was about 18 miles an hour. That was scary, I will tell you. Um, but if we want to know exactly how fast we're going in any given moment, we have to divide those moments up. And if we divide them up even smaller and even smaller, we get better approximations to that line. And if we make that delta t shrink down to zero, then the limit delta x over delta t in the limit that delta t shrinks to zero, this becomes that actual derivative. That is, at any given point, it's the slope of that curve. And so average velocity, average acceleration, all of those are very useful. But we know just from experience, just from everyday life, that things can happen instantaneously that are very different. And we often want to know what the instantaneous speed is, or velocity, or acceleration is, as opposed to the average. Um, the other thing that we did was that we had two different definitions for average velocity. Basically, the final position minus the initial position over the time it took to do that, and the final velocity plus the initial velocity divided by two. Those two things are the same, and it's from that that we can derive the kinematic equations of motion. That's in a separate video, so I'd encourage you to look at that. Okay, what else do we got? All right. I think reviewing the equations would be beneficial. I think that is also very true. And what I would recommend is, again, 3x5 card every day in class. Write on one side the topic for the class. So on Tuesday, it's projectile motion. And on the back side, write down every equation that we use. And you'll find out that it's not many. In the course of this class, it probably amounts to about 20, 24 or so questions. Um, Okay, we've already answered that. Derive the equations, that's in a separate video. More questions on the IDEA format. We also have a link from the book that describes that, so please look at that. I've also graded the GPS problems, and you can see how I wrote each step of the interpret, develop, evaluate, and assess. Okay, more IDEA stuff. Some of this is clarification on what numbers to plug in for V naught, X naught, and so on. That's going to take practice. And so I think some of that's context with the questions, and some of it is just coming to office hours. And we'll be very happy to help you. Okay, have any? How can acceleration be negative the moment the object is slowing down? Okay, so I think there's questions about how acceleration is kind of a weird thing compared to velocity. So position, displacement, acceleration, and velocity are all vectors. You can have a negative acceleration and not slow down if you're moving in the negative direction. That's all that meant. So suppose the negative direction is defined as going to the left, and you're accelerating to the left. You're going to speed up to the left, right? If you are moving to the right and your acceleration is to the left, you're going to slow down, right? If you're moving to the left, so negative velocity, and your acceleration is positive, you're also going to slow down. And if you have enough acceleration, eventually turn around and go in that direction. That's all we mean, is you got to be careful about the direction of the accelerations, why physicists try and avoid, say, deceleration, because it's not necessarily the case that you're going to brake. You might actually be speeding up if the direction of that, if negative acceleration is also in the direction that you're moving. Um, Questions using v squared minus v naught squared equals 2ax minus x naught. Please look at the GPS solutions and the derivation of the kinematic equations of motion. Clarification on when to use x hat. That's a great question. I would, as a general rule, you can use x hat, y hat, z hat Anytime you're dealing with a vector, in 1D it's not quite as important. You'll see on Tuesday that the one of the wonderful things about doing things in multiple dimensions, so you can break it apart, and the motion is connected in a very subtle way, very cool way. But also you can do two problems separately. Motion in the X and motion in the Y are different. And especially in the case of projectile motion, motion in the X direction is often just a constant speed, whereas motion in the Y direction is accelerating because of gravity. Um, Understand there can be acceleration even though there is no velocity due to direction, but I don't fully understand how to find acceleration from no velocity. That's a very subtle, very cool question. And where that comes from, so the question is really asking if v is zero, can you have acceleration? And the answer is acceleration necessarily zero? And the answer is no, not necessarily. And the reason why that's true is that you're only taking a snapshot of the object in its motion. Say at the top, for example, hit a ball or take something. I don't know. I have a fuzzy 20-sided dice. If I throw it up in the air, the moment that it's at its highest, its v is equal to zero, but it's constantly being accelerated downward. If it weren't being accelerated downward, it would just go and never come back. So this is a case when you throw a ball up in the air that there's always acceleration everywhere along its path, but at some point its v is equal to zero. Now, how do you find that acceleration? You can't find it in the moment because that's just a snapshot. You need to have the actual expression that x of t. In order to find that. If you have x of t, then you can take the derivative of x of t and find v of t. And if you have v of t, you can take the derivative of v of t and find that a of t, but then you evaluate it at that moment where v is equal to zero. So it's a really interesting, subtle question that you've asked. Thank you for asking that. Let's see, some more derivation again on YouTube. Let's see. Underdog graphs. We went over that. Would love to know how the introduction of gravity changes the moon problem. Hmm. Well, take more physics is the short answer. The somewhat less short answer is that it's complicated because you get accelerated. So there's acceleration from the Earth and acceleration from the moon. And you have to take into account that you've got two forces that are acting on the rocket itself. And that makes the problem really interesting. Um, if you think about landing on the moon, you can't just turn around and stop. You get close enough to the moon, you feel the moon's gravity. The moon's gravity reaches out to us just as we reach out to the moon. Um, but you need to have landing rockets, otherwise you would just smash into the surface of the moon. But that is beyond what we're doing in this class, so I would suggest you take more physics. I would suggest you all take more physics. Anyway, that is all of the questions that you asked this week. Thanks for being in our class. We had a great time, and you guys are doing great. Next week, we're going to be doing two-dimensional kinematics, that is projectile motion, and starting just the taste, the barest little taste of forces and dynamics. So after 3 classes on describing how things move from kinematics, we're going to go into dynamics and start answering why things move. And that, dear friends, depends on the force. May the force be with you. All right. Thank you so much. And I will see you on Tuesday.